Hello everyone, good morning. So I think I'm audible, right? So good morning. Actually, first of all, very sorry that I couldn't take class for the last 20 days. That is mainly due to the health issues, right? So I'm recovering now. So I thought of planning to resume the classes once again. So we will do modern algebra and analytical geometry simultaneously, right? Because both are very vague and also very important topic in UPSC point of view. So I thought of completing these two vague chapters first, then we will have all easy chapters only, right? And also, since I have given you some 20 days break, you might have forgotten some concepts in analytical geometry, right? So I want you to revise all those concepts: direction ratios, direction cosines, planes, spheres, all that. Then only we'll have some continuation. If I start directly means without revising the concepts, you may not follow fully, right? So next 2 or 3 days, take time to revise all the concepts. Then for the next 2 to 3 days, we will focus on modern algebra. After that, we will do analytical geometry and modern algebra simultaneously, right? Okay. Modern algebra comes in paper 2. Paper 2, very important. This comes around 40 to 60 marks, right? It is theoretical, right? It will be not be problem oriented. It will be theory based only, right? You will have theorems, you will have corollaries and so on, right? It is purely based on theoretical only. It will be difficult, but if you follow, it will be easy, right? If you think it is difficult, it will be difficult only. So before starting itself, assume that it is easy only. Then only you will have good clarity about the subjects, right? I'll help you very easy, very interesting also. Just understand the definition and examples. Theorem proof you can itself prove. Just want to understand the definition and example more clearly to understand all the proofs in modern algebra. I'll give you lots and lots of examples, right? Lots and lots of examples to make you the concepts clear. Just follow my notes for modern algebra. That is enough, right? Just follow my notes. Don't follow any books. Just follow my notes for modern algebra, right? This is the introduction about modern algebra. So if you see the syllabus, it is mainly grouped into two parts, right? Group theory and ring theory. Group theory and ring theory. Um, Group theory and ring theory, right? So group theory will have groups, subgroups, cyclic groups, cosets, and Lagrange's theorem. Normal subgroups, quotient groups, homomorphisms, isomorphisms, and permutation and Cayley's theorem. Right? This is the syllabus for group theory. And the ring theory will have ideals, integral domain, Euclidean domain, UFD, and so on. Right? Very easy only, but it is theoretical. Right? It will not be problem oriented. It is theoretical only. Right? Okay. So see, everything is just extension. You just have to be thorough with the group to understand the concepts of quotient field. So everything is an extension, right? So from one step, second step, third step, fourth step, and so on. So you need to be very strong in the first step. Then only you will understand the last step, right? So groups is the very fundamental for all. It is fundamental for ring theory. It is fundamental for field theory, and also it is fundamental for vector space also. Right? In linear algebra, you would have studied vector space, right? For that also, this is very elementary topic that you need to come very easy only, right? I'll give you lots and lots of examples so that you will have more clarity and interest in the subject, right? So in this class we're going to start with groups, right? So we're going to define what is meant by groups. I'm going to give you lots and lots of examples for groups, and in the upcoming classes we will see subgroups, cyclic groups, and so on, right? So we will extend this. So first we'll start with groups, right? Is there any doubt before getting into today's class? So it will be around 40 to 60 marks from modern algebra, and this comes under paper 2. Yes. So first, what we will do is we will and the book that I'm going to follow. I'm going to follow two books for modern algebra. The first book is Modern Algebra Krishna series. Right? That is Vasista's book, Krishna series Modern Algebra. And the second book is this is the book, A Course in Abstract Algebra, Vijay K. Khanna and S. K. Bambri. Right? This is one of the best books for modern algebra. But you just follow my notes, right? My notes will be based on these two books only. A Course in Abstract Algebra by Vijay K. Khanna and Modern Algebra by Vasista series, right? So this is the two books that I'm going to follow for giving you notes, right? Yes. So we'll start. So first we'll define what is meant by a group, and then I'll give you lots of examples for groups, right? Okay. Definition, right? So group. See, you just have to understand, right? Very, very easy. You just follow the class and follow my example. Take a proper notes. That is more than enough, right? Okay. So we'll start. See, we're going to have a non-empty set G, right? A non-empty set G. A non-empty set G, right? So we have a non-empty set G, right? So G is any non-empty set. It should be non-empty, right? A non-empty set G together together with, see, I'm not going to follow. I'm just going to write what I know. That's it, right? So since I have been taking modern algebra for many years, if you have good practice, you can construct proof in your own, right? I'll give you two or more techniques for the same proof. Then you will have more clarity about the subject, right? So since I have some experience in this subject, I'll give you more clarity on this subject, right? I have more experience in this topic. So non-empty set G together with the binary operation star, with the binary operation star. See, we have a non-empty set G and a binary operation star. This binary operation can be anything. It can be addition, it can be multiplication, it can be composition, it can be modulo operation. So there are many binary operations that we will come to know in the later classes. It is a binary, a set G with binary operation. A binary operation can be addition or multiplication or composition, or there are many binary operations, right? So we have a non-empty set G together with the binary operation star is set to form a group. Is set to form a group, right? Is set to form a group if it satisfies the following four conditions. That's it, right? If it form a group, if it satisfies the following four conditions. The first condition is said to be closure. See, we have a non-empty set G, right? So this is a non-empty set G. Since this is non-empty, this will have at least one element. So no, it is non-empty. So let us say this has some element A, this has some element B, this has some element C, and so on. This is non-empty, right? So first property is called closure property, right? Closure. So what closure says is you take any two elements in G, right? You take any two elements in G. So let A comma B belongs to G. So you take any two elements in G, right? So you take any two elements in G, then A star B also has to be in G. For all, this is very important. For all A comma B belongs to G. So whatever two elements you take, you just compute A star B. What is star? It's a binary operation. So binary operation is fixed in the beginning itself. If it is plus, then A plus B has to be in G. If it is multiplication, A into B has to be in G. Right? This star should be defined first itself. Here the binary operation is plus. Here the binary operation is multiplication. It has to be defined in the first itself. And based on that, you need to put star can be anything. It can be plus. If it is plus, it is plus for all. If it is multiplication, it is multiplication for all. It should be defined in the first itself, binary operation. Okay, so this is closure. What closure says? You take any two elements, A star B should be in G. Star is a binary operation that you are doing, right? Okay, this is called closure property. Now, second property is called associative property, right? Associative property. You take any three elements in G, right? You take any three elements in G. This says belongs to, right? This means belongs to. I'm taking three elements in G. A star B star C is same as A star B star C. That is, you perform A star B first. With this result, you perform with C. Here, you are performing B star C first, and then you are doing A star with this result. Both has to be same. If it is true, it is associative property. See, in set theory itself, you would have studied these topics, right? When you are doing set theory in ninth and 10th standard, they will give you three set A, B, C, right? In set theory, the operation binary operation will be union there. It will be union there in set theory. So you would have studied that A union B union C is same as A star B. Sorry, A union B union C. You remember that? Because union is also on binary operation. Intersection is also on binary operation. For some set, right? Okay. Intersection need not be binary operation for some set. Okay. So you would have studied, right? And you would have also noted, right? A plus B plus C is same as A plus B plus C and so on. Okay. Okay. Now third is existence of identity, right? So what is this is for all A comma B, right? For all ABC belongs to G. For every ABC belongs to G. It has to be true for whatever it has to be true for arbitrary elements. It has to be true for all, right? Okay. So existence of identity, right? Um, existence of identity for all A belongs to G, there exists. See, if this is means there exists, right? An element, there exists an element E in G, right? There should exist an element E, that E should satisfy the property that A star E is same as E star A is same as A, right? So there, the ID element is unique. ID element is unique. There should exist an element E, right? E can be anything. E can be anything. It is a number, right? Just for labeling here, I'm denoting by E. What if you perform operation with E with any element? It has to be that element again. That is A into E. If your operation is multiplication, A into E has to be E again. What will be E then? A into E. If your operation is multiplication, if your operation is multiplication, A into E has to be A again. What about this E? This E will be 1. That means if your operation is multiplication, ID element will be 1 because A into 1 will be A for all element. Suppose if your operation is addition, A plus E has to be A again. In that case, E will be 0 because A plus 0 will be A. So if your operation is multiplication, your E will be 1 if your system is number system, right? Okay. We will discuss more. We will discuss more. Okay. We will discuss this more later. So that means whatever element A you take, if you perform operation with the E, A has to be again. It has to be A again. Then this E is called ID element, right? ID element will be unique, right? It is unique E. This ID element is unique. So I'll give you more examples that you will have more clarity, right? Okay. Now fourth is existence of inverse. Existence of inverse. So for all A belongs to G, there exists an element, A inverse. For every A, there should exist some other element. Let us call that as A inverse, such that if you perform binary operation with A and A star, it has to be E, or A star A has to be E. Then this is called inverse of A, right? It is called inverse of A. In matrix, you would have studied. They will in 12th standard they will give you a matrix, and you will find the inverse for that matrix. And remember that you will be using the formula A inverse is equal to 1 by determinant of A to 1 joint of A. That means if A, you can find A inverse with that. If you multiply A and A inverse, it will give you an ID element. For matrix, the ID element is ID matrix. That we will discuss more, right? Just I'm giving you some connection between school level and this level. That's it. So that's it. So for every A, for all A in G, there exists an element A inverse. For every A, there should be some other element such that if you multiply this element and this element, it will give you an ID element. Right? What is ID element? Whatever element you take, if you multiply with that E, it will give you A again. Then this E is called ID element. ID element you can find from here. From here, you can substitute E so that you can find A inverse. So if a non-empty set G, a non-empty set G together with the binary option star is said to form a group if it satisfies the following four conditions, right? So I'm going to write like this: G with respect to binary operation star is set is said to form a group, said to form a group if it satisfies the above four condition. It satisfies the above four conditions. See, is there any doubt in this definition? See, we will discuss more examples, right? We will have more clarity. We will discuss many more examples for a group. If you know large number of examples, then everything will be very easy for you. No large number of examples, right? You will discuss. I'll discuss many examples, right? Many unknown examples, many known examples, many unique examples. I'll give you more clarity. So very simple, right? So we have a non-empty set G. There will be some elements. If those elements satisfies these four conditions, then we say it is a group. So a binary operation you need to fix in the beginning itself, right? So whenever you are taking the set, you need to fix the binary operation. It is star. Star means it is in general I'm writing star. It can be anything, right? Okay. Now I'm going to introduce one more definition, which is called abelian group. Right. So Abel, some great mathematician, he is the one who coined abelian group. Very simple. A group is said to be a abelian group. Already it is a group. That means what? Already that set satisfies these four conditions. A group G, a group G is said to be an abelian group. Is said to be an abelian group if it satisfies commutative property. It satisfies commutative property. That is, A star B is same as B star A for all A comma B belongs to G. Right? You know this commutative property, right? A plus B is equal to B plus A if your binary operation is plus, right? Okay. So very simple. So we have seen two definitions. See, if your group satisfies only the first two condition, but not third and fourth, then it is called semi-group. If your set G satisfies only these two conditions, that is closed and associative, but it doesn't have ID or it doesn't have inverse, then we say that set G is semi-group. Semi-group. If your set G satisfies the first three conditions alone, that is, it has closure, it has associative property, it has ID element, then we say that set G is monoid. And if it satisfies four condition, it is group. And if it satisfies commutative property, it is abelian group, right? So if it satisfies only these two conditions, if it satisfies only these two conditions, it is called semi-group, right? If it satisfies only the first three conditions, it is called monoid. And if it satisfies four conditions, it will be a group, right? If it satisfies only the first two condition, it is semi-group. If it satisfies the first three condition, it is monoid. And if it satisfies four condition, it will be a group. Is it clear up to now? Can we do some examples? So whenever you need to say it is a group, you need to tell that it has, see, very simple. In exam point of view, they will give one set, they will give one binary operation. Show that it is a group. Even if you don't know anything, you just write these four definitions. They will give you 50% of marks. That's it, right? They will give you a set G. They will give the binary operation. You need to prove it is a group. That means it has to satisfy these four conditions. Even if you don't know anything, write the definition. Take any two elements in G. Say that A star B is in G. Give some examples. Closure is over. For associative, take three elements in G and write this definition. Prove this. Very easy. Right? In modern algebra, even if you don't know anything, right, apply the known definitions and try to prove, you will get almost 50 to 60% of marks. Right? That is the main thing about modern algebra. If you have some problem oriented means, you cannot write a story. But in modern algebra, you can write some stories based on the definitions and examples. You can try to prove. You will get almost 50 to 60% of marks even if you don't know anything. Okay. Okay, so I'll give you many examples, right? So for the next 1 hour, 1.5 hours, I'm going to give you more examples, so that you will have more clarity. First is example one, right? Example one. Um, and first we'll discuss about the number systems, right? We'll discuss about the number systems, which number systems forms the group with respect to some operations. Okay, so first we will have first example, natural number with respect to the binary operation plus. Natural number with respect to the binary operation plus. Here our set G is n, right? Here, see, first itself you need to denote the binary operation. I said it right. You have to predefine that binary operation in the beginning itself. Okay. So what is our set G? The set G is natural number. So that means this has 1, 2, 3, 4, and so on. Right? And so on. So you need to check whether it forms a group or not. Right? Okay. The first is closure. First is closure. So what is closure? For A comma B belongs to G, A plus B has to be in G, right? Because it is A star B, but our star is plus here. Now what is AB? AB is in G. That means you take any two arbitrary natural number. So A is natural number, B is natural number. So surely sum of two natural number is again natural number. Yes or no? Sum of two natural number, sum of two natural number is again a natural number. Yes or no? You take any 3 plus 4, 7. 7 also is in G. 1 plus 4, 5. 5 is also in G. What is G? G is our n. So it is closed. Right? So it is closed. Okay. Now second is associative. Associative. For A comma B comma C belongs to G, A plus B plus C has to be same as A plus B plus C. This is obviously true, right? See, sum of two natural number, natural number. Natural number plus natural number, natural number. Natural number plus natural number, natural number. You are just shifting the order of addition. It will not affect. So it will be closed, right? Our example, for example, you just take A to be equal to 1, B to be equal to 2, C to be equal to 3. You just write theoretically, right? You just say, see, B plus C is natural number, A, B, C are natural number. Obviously, this will be true only, right? If not, you just take some arbitrary A, B, C. What about A plus B? A plus B plus C is same as A plus B plus C. And you can see 3 plus 3 is 6. Is 6. So it is true for all A, comma B, comma C. See, actually you should not prove like this. I'm taking some ABC, but it has to be true for all ABC. So in exam point of view, I'm just telling you to approach this method. You just say it is naturally, it is true, right? Since it is an infinite set, by definition, it has to be true for all A, comma B, comma C. But here I have taken only one A, comma B, comma C. With this, we cannot say it is true for all. So in exam point of view, you just go by this method. Just for example, I'm saying they are equal. But I'm saying it is equal for only taking one ABC. But it has to be true for all A, comma B, comma C. It is an infinite set. You cannot prove for all A, comma B, C. So it has to be, you have to generalize this. You just say by words, that is enough. Okay. Now the existence of identity. So what is the definition of identity? For all A in G, there exists an element E. There exists an element E in G such that A plus E to be same as E plus A has to be A. What about E here? So you need to add an element E so that you have to get A again. What will be that number? What will be that number? See, for example, if I take 2, 2 plus what is 2? 2 plus what is 2? I'm just looking for a comment. If I take 2, but 0 is not in the set, yes or no? Actually, E has to be 0, but that E has to be in G. But here, there is no 0 in this G, right? For example, if I take 2, 2 plus what is 2? This has to be 0, but this G, E has to be in G, but there is no G here. So there is no ID element. 0 is the ID element, but it doesn't belong to the set because there exists an element E that has to be in G, but here there is no 0 here. So that means there is no, actually 0 is the one that satisfies this condition. 0 is the one that satisfies this condition, but 0 doesn't belong to G. G is the natural number. So there is no ID element. There is no ID element. If there is no ID element, obviously inverse will not be there because inverse is based on ID element only, right? A into A inverse has to give you E, but there is no E here itself, right? Therefore, you don't need to check for inverse. Inverse doesn't exist. So that means natural number with respect to addition forms a semi-group, but it doesn't form a monoid or it also doesn't form a group. Is it clear? So what is the conclusion? Natural number with respect to addition. What is the conclusion? Natural number with respect to addition doesn't form a group. Doesn't form a group. See, if it is a group only, then we can go for abelian group. If it is a group only, then we can go for abelian group. So that means we don't need to check for commutative property here. Form a group, it forms a semi-group. Forms a semi-group because it satisfies the first two conditions, right? Okay. Now we'll go for next example. Natural number with respect to multiplication. Right? So if it is multiplication, I will be putting a dot. Now we will check for all those properties. So first is closure. Closure. So for all a comma b belongs to G, a into b has to be in G, right? For all a comma b belongs to G. Obviously, product of two natural number is again a natural number, right? So because AB is in G, so what is G here? So G is natural number, so which is 1, 2, 3, and so on. So product of two natural number, product of two natural number is again natural, right? So therefore, obviously, A into B will be a natural number and G is our natural number, right? For example, if you take 2 and 4, 2 into 4 is 8, 8 is again natural number. So obviously, the product will also be in the set only. And again, it is associative also. Also, you can easily prove that A into B into C is same as A into B into C. The exam point of view, you just say it is obvious, it is clear that it satisfies associative property. That is enough, right? Or if you have some time, for example, you take ABC to be three number and just prove that LHS is equal to RHS. Okay. Now, existence of identity. So what is the definition for all? See, every time you have the right definition, right? Then only we'll have very good practice. Every time you have that definition. So for all A in G, there exists an element, E in G such that A into E is same as E into A is same as E is same as A again. Is same as A again. What about E? What about E? 2 into something is 2. That something has to be 1. Right? That something has to be 1. So obviously E has to be 1 here. And this 1 is in the set G. So therefore 1 is the ideal element. So therefore, 1 is the, see the previous example, 0 is the ID element, but 0 doesn't belongs to G. So you said that 0 doesn't have ID. But natural number with respect to multiplication, it has ID element. Because there is an element 1 in this, such that 3 into 1 is 3, 4 into 1 is 4, 100 into 1 is 100. So whatever element you take, if you multiply with that element, it will give you that that element back again. That means C has to be 1 if your system is number system and if your operation is multiplication. So therefore 1 is the ID element is always unique. We will prove all those. So 1 is the ID element because if you take E to be equal to 1, it satisfies this definition. So it has ID element. Existence of inverse. Existence of inverse. What is the definition? So for all A belongs to G, there exists an element A inverse in G. I'm going to put belongs to G here. There exists an element A inverse in G. There exists an element A inverse in G such that A into A inverse is same as A inverse into A is same as A again. See this is a normal multiplication. What about A inverse? Sorry, this E. So what is E here? E is 1. That means A into A inverse has to be 1 year because we know E is 1 for this set with this binary operation. So that means what about A inverse? It has to be 1 by A, right? Because 2 into what is 1? It is 1 by 2. 3 into what is 1? It is 1 by 3. 5 into what is 1? It is 1 by 5. Yes or no? So that means this implies A inverse has to be 1 by A. Then only we will have A and A will get cancelled. That will give you 1. For all A, there should exist A inverse. If I take 2 in G, but 2 inverse is what? 1 by 2. This doesn't belongs to G. 1 by 2 is not natural number. Yes or no? So that means inverse does not exist. See, it has to be true for all A. If you want to say not means you just give you one counter example. That is enough. Right? By definition, for all A, if you give me one A which it doesn't work, definition fails. That's it. That is the very important beauty. If you, that is what I will be saying. So disproving is very easy in maths. Disproving is very easy. If you give a counter example, that's it. You just have to give a counter example that you can do in 10 to 20 seconds. But proving is difficult. Disprove is very easy. So for disproving this, I'm just saying that I'm taking element of 5. 1, 1 by 5 is the 1 by 5 is the inverse, but 1 by 5 doesn't belongs to G. Because A inverse, that element should also be in G. So therefore, inverse does not exist. So that means natural number with respect to multiplication forms a monoid. It doesn't form a group because it fails to satisfy inverse definition. So conclusion is natural number with respect to multiplication doesn't form a group. It is monoid because it has satisfies closure, associative, and existence of identity. Is it clear up to now? Can you want to some? Is it clear? Gopal Shah, why this not monoid? This monoid only. Okay, so we move on to next examples. The third set of all integers with respect to the binary operation. So from now on, I'll be a little bit fast. Okay, because you know how to prove closure. Uh, Everything is visible, right? Not getting any comments. If it is clear, you just say it is clear so that I can carry forward with good. Okay. So integers with respect to addition. So here you will set G is integers. This will have 0, less or minus 1, less or minus 2, less or minus 3, and so on. Right? Now we will check. See, I'm just going to tick that's it, right? So it will be closure because A and B are integer. Sum of two integer is again integer, right? Sum of it is closure for all. So for all A comma B belongs to G, A plus B will also be in G because sum of two integer is again integer. Not going to write it. Sum of two integers is again integer, and again it will be associative. Will be associative because A plus B plus C is same as A plus B plus C. And what about existence of identity? What about existence of identity? For all for all A belongs to G, there exists an element E in G such that A plus E has to be A is equal to E plus A has to be A again. So this implies E has to be 0 and the 0 is in the set G. See, for natural number with respect to addition, 0 is not there. But here, but here it is 0 is here. Right? So therefore, E is equal to 0 is the ID element. Right? E is equal to 0 is the ID element. And what about existence of inverse? See, for all A belongs to G, there exists an A inverse in G such that A plus A inverse is equal to E, that is same as A inverse plus A. Now this implies A plus A inverse is 0 because E is 0 here. That means A inverse has to be minus A. Yes or no? 2 plus what is 0? 2 plus what is 0? It is minus 2. 3 plus what is 0? It is minus 3. 100 plus what is 0? It is minus 100. So obviously, if A in G, minus A will also be in G because it is integer only, right? If 3 is in G, minus 3 will also be in G. That means this minus A is the A inverse and this belongs to G for all A. For all A. So therefore, inverse exists. So therefore, inverse exists for each element or all elements. What is the inverse for 4? Minus 4. Inverse for 100? Minus 100. Inverse will be different for each elements. Inverse for 20? Minus 20. Inverse for 1 lakh? Minus 1 lakh. So inverse exists for all elements. So that means what? So we have closed, we have associative. E is equal to 0 is the ID element. For all A, minus A is also in G. So therefore, integers with respect to addition forms a group. And also, A plus B is same as B plus A. It satisfies commutative property also, right? A plus B is same as B plus A if A and B are integer. So that means it also forms an abelian group, right? This is the first set that forms a group for all A, right? So fourth is integers with respect to multiplication. Again, it is closure satisfies product of two integer is again an integer, so it will be closed. Again, associative because A into B into C is same as A into B into C. You can write that. And what about existence of identity? So what is the definition? For all A belongs to G, there exists an element E in G such that A into E is same as E into A is same as A again. So that means A into E is equal to A. This implies E has to be 1 and this 1 is in G. G is the integer. So 1 is the ID element. What about inverse? existence of inverse. For all A belongs to G, there exists an element A inverse in G such that A into A inverse has to give you E. So this implies A into A inverse is equal to 1. This implies A inverse is 1 by A. But again 1 by A is not integer. If you take A to be equal to 2, A inverse will be 1 by 2, but 1 by 2 doesn't belong to G because integer does not contain 1 by 2. So if you give you one example, that is enough to prove it is inverse does not exist, right? It has to be true for all A. For all A, 1 by A should be in the G. But I can give I given you one A for which 1 by A is not in G, so inverse does not exist. So it doesn't form a group, right? So integer with respect to multiplication, not a group, doesn't form a group, right? So fifth, here up to now, so we have seen natural numbers and integers. Just two more, uh, rationals, irrationals, and real number. After that, we will give you some examples of it. Okay, so fifth, rational number with respect to plus, right? Rational number with respect to plus. So again, it will be closed because for all A comma B belongs to G, A star B has to be in G. Star is plus here, so A plus B. So sum of two rational number is again rational. Sum of two rational number is again rational. You just have to write that. I'm not writing this, right? Write the definition for all A comma B belongs to G. A star B has to be in G. Star here is addition. So A plus B has to be in G. AB is in G. So that means A and B are rational number. So A plus B, sum of two rational numbers again rational number. Okay, closure. So associative. So again, just say it is true. Existence of identity. So by definition, for all A belongs to G, there exists an element E in G such that A plus E is same as E plus A has to be A again. Implies E has to be 0 and 0 is in rational number. So E is equal to 0 is the ideal element. What about existence of inverse? So for all A belongs to G, there exists an element A inverse in G such that A plus A inverse is equal to A inverse plus A is equal to E and E is 0. This implies A inverse has to be minus A and minus A is in G. So whatever A you take, minus A will also be in G, right? Because A is a rational number. 1 by 2 minus 1 by 2 will be there. 3 minus 3 will be there. So belongs to G, right? So therefore inverse exists. And also it is commutative also. It is commutative also because A plus B is same as B plus A for all A comma B belongs to G. So therefore rational number with respect to plus forms a group, forms an abelian group also, forms an abelian group, right? Now we'll go for sixth example. Rational number with respect to multiplication. What about closure? Product of two rational numbers again rational number is true. Existence of identity. So for all A belongs to G, there exists an element E in G such that A into E is same as E into A is same as A again. Implies E has to be 1 and 1 is in G. So therefore, 1 is the ideal element. In most of the cases in number system, right? In number system, I'm stressing number system. In most of the case in number system, uh, with respect to multiplication, 1 will be the ideal element. With respect to addition, 0 will be an ideal element in number system. Okay. Existence of inverse for all A belongs to G, there exists an element A inverse in G such that A into A inverse is same as A inverse into A is same as E. This is the definition of inverse. So A into A inverse has to be 1 because E is 1 here. That means A inverse has to be 1 by A. Is it true? Is 1 by A belongs to G for all A belongs to G? Is it true or not? If 3 is rational, 1 by 3 will be rational. 1 by 3 is 1 by 3 is the inverse and 1 by 3 will be a rational number. If 4 is rational, 1 by 4 is the inverse. If you take 5, 1 by 5 is the inverse and 1 by 5 is rational, right? Uh, can I say inverse exists? Yes or no? Can I say inverse exists? Sir, by definition, for the existence of identity should be there. Yes, it is exists only for non-zero element. It has to be true for all A. But if I take A to be equal to 0, if I take A to be equal to 0, what happens? 1 by 0 is undefined, right? That is what I'm stressing. That is what I'm writing for all. It doesn't give you more importance. But if you this line is very important, right? It seems to be not important for you. Just without knowing this, you will be writing for all. But this is the thing that is making the entire definition failure. It has to be true for all A, but I have given you one A, which doesn't satisfy this. That means inverse doesn't exist. Even though it satisfies for billion elements, doesn't satisfy for one element here, right? So if A is equal to 0, 0, this belongs to G, right? This belongs to G, but A inverse is 1 by 0, doesn't belong to G. That means if A is 0 here, inverse doesn't exist. But what happens if I remove 0 from this set? What happens if I remove 0 from this set? See, for all A in G, so 0 is in G. That is why 1 by 0 is not in G. If 0 itself not in G, then it will be a group, yes, or no? So if I remove 0 from this set, I'm removing an element that is in the set of all rational numbers. I'm removing 0. Then it will form a group with respect to multiplication. Because 0 is the only element that is troubling us. If I remove 0 from the set, I cannot take 0 from the set. Because for a inverse, A has to be in G. but 0 is not in G because I removed 0 from the set. So that means, first we will conclude this. Rational number with respect to dot, not a group, because it doesn't have inverse. But, right, I'm defining a new set now. I'm going to define a new set now. I'm going to denote this as Q star, right? Q star. So what is Q star? Q star is Q star is all rational numbers except 0. So I'm just removing 0 from that set. Then it will be an abelian group. It also has commutative property also, right? A into B is same as B into A. For all A comma B belongs to C. Is it clear? So whenever you see Q and Q star are different. So Q is all rational numbers, but Q star is rational numbers excluding 0. All rational numbers excluding 0. So here you can see inverse exists for all non-zero element. 0 is the only element that is doubling this. So this consists of all non-zero, all non-zero, yes, all non-zero natural rational numbers, right? Okay, so seventh, we're going to finish very soon, right? Rational number with respect to plus forms an abelian group. Rational number with respect to multiplication doesn't form a group, but rational number except 0 forms an abelian group with respect to multiplication. Now set of all irrational numbers, right? Set of all irrational numbers with respect to plus, right? Set of all irrational numbers with respect to plus. So R minus Q is real number minus rational number. That will give you irrational number. So set of all irrational numbers. Yes, is it a group? Is it closed? Is it closed? What is closure? For all A comma B belongs to G, A plus B belongs to G. So I'm taking two irrational number. Is the sum of two irrational number is irrational? Sum of two natural number is natural. Sum of two rational is rational. Sum of two integer is integer. Is the sum of is the sum of See, first we'll go step by step, right? First we'll go step by step. Idea exists, right? Um, zero is rational or irrational. Okay, that will come to later. Is the sum of two irrational is rational? That is the question, right? See, if I take a to be equal to 2 plus root 2, right? If I take a to be equal to 2 plus root 2, and if I take b to be 2 minus root 2, so you can see a and b both are irrational number only, right? Because we know sum of irrational plus rational is always irrational. So A and B both are irrational only. But what about A plus B? A plus B is what? So 2 plus root 2, 2 minus root 2. It will give you 4. And 4 doesn't belong to G. Because 4 is not an irrational number. 4 is a rational number. So that means the closure itself fails here. Right? Closure itself fails here. Sum of two irrational number need not be irrational. Right? Sum of two irrational number need not be, right? Need not be. It can be or it may not be. If I put instead of 2 minus root, if I put 2 only, then 2 plus root 2 plus 2 will be 4 plus root 2. That is irrational, but it has to be true for all a comma b belongs to G. I have given you one ab which doesn't satisfy closure property. That means it is not true for all. So sum of two irrational number need not be irrational. So closure itself fails. You don't need to check for any other conditions, right? You want to check for any other condition. Okay. Now we'll go for eighth. Now, what about set of all irrational number with respect to multiplication? Is the product of two irrational is irrational? Just give me a counter example, right? Is the product of two irrational is irrational? See, you take a to be root 2, b to be root 2 again. You take any two element, I'm taking both element to be root 2, root 2. Now, what about a into b? So, you can see a and b are irrational, but a into b is rational. It belongs to G, right? So, therefore, it's not closed, right? It is not closed. So, 9, set of all real number with respect to addition, it forms an abelian group, right? Because we already know integers forms an abelian group with respect to addition, rational number forms an abelian group with respect to addition, real number also. I don't want to prove this, right? Sum of two real number is real number. Real number is very strong. Sum of two real number is real number. Associative property holds. E is equal to 0 is the ID element. For every a, minus a is the inverse, right? I'll just give you an int, right? I'll just give you an int. So it is closed. It is closure. It is associative, and ID element is E is equal to 0 is the ID element because 0 is in real number. Inverse is, so A inverse is minus A, and minus A is also in G. And also abelian group also, right? Because A plus B is same as B plus A for all A comma B belongs to G. So therefore, real number with respect to addition forms an abelian group. Forms an abelian group. And similarly, what about real number with respect to multiplication? Again, 0 is the only element that will be troubling here, right? It is closed. It is closed. It is associative, and ID element is E is equal to 1. But what about inverse? If you take A to be equal to 0, A inverse is 1 by A, 1 by 0 does it belongs to G. That means real number with respect to dot, not a group, right? Not a group. But if you remove 0, but if you remove 0 from uh, real number, it will be a group, right? Note, R star comma dot forms an abelian group. Forms an abelian group. Is it clear? Is this page is clear? See, with respect to multiplication, R for every element there will be inverse. It is same as the one for that we discussed for rational numbers, right? With respect to multiplication, it will be here also. So if we take 0, 1 by 0 will not be in G. So therefore, with respect to multiplication in number system doesn't form any, no number system forms a group with respect to multiplication, right? But if you remove 0 from that set, then the real number and rational number will form a group with respect to multiplication. I'll repeat, in number system, no number system forms a group with respect to multiplication. But if you remove 0 from real number and rational number, then it will form a group, right? So similarly, complex number with respect to addition forms a group, and complex number with respect to multiplication doesn't form a group, right? So similarly, just make a note of it, right? So already again 10 example. So 11th example is complex number with respect to plus forms an abelian group. You just take this exercise, right? Because see here every element is of the form a plus ib, right? So complex number is a plus ib, ab are real number. So sum of two complex number is again complex number, so it will be closed associative holes. And again zero is ideal element. 0 plus I zero, right? 0 plus I zero is the ideal element. What is the inverse of a plus ib? Minus of a plus ib. That is the inverse. A plus ib inverse is minus of a plus ib. This is again complex number only. So it will be group. And what about complex number with respect to multiplication? Not a group because 0 we don't have inverse. But if you take complex number with respect to multiplication, that is C star. C star forms an abelian group. Right? So what about ID element? ID element is 1 plus 0 I is the ID element. Right? And inverse is 1 divided by A plus IB. This is the inverse. Right? And here the ID element is 0 plus 0 I, and inverse is minus of A plus IB. That's it. Is this examples are clear? See, all these is based on number systems, right? You just make a table for number system. You can easily prove all this, right? Is these 13 examples are clear? Is these 13 examples are clear? See, all 13 examples are infinite group. Why it is infinite group? Because our set G is infinite, right? All 13 examples are infinite group. Why? Because our the set G is infinite, right? Okay, I will go for 14th example. So I'll give you some examples of finite groups now, right? So there are also we need to discuss about more infinite group. So matrix is also an infinite group. That will be group, right? Matrix. Your set G consists of all those n by n matrices. That will also form a group that we'll discuss later. Now I'll give you an example of finite groups, right? So all 13 examples are infinite group because our set G is infinite. Now we'll give you an examples of some finite groups. Right? Some finite groups. All 13 examples are infinite group, right? Okay. A set of all solutions of x cube is equal to 1 or z cube is equal to 1 forms an abelian group. See, what is the solution of z cube is equal to 1? It is a cube roots of unity, right? It is a cube roots of unity. That are called solutions of z cube. What is the solution of z cube is equal to 1? A cube minus b cube. A minus a square plus b plus b square. implies z is equal to 1 or z square plus z plus 1 is equal to 0. Solve this. So z is equal to minus b plus or minus root of b square minus 4ac divided by 2 times a. So minus 1 plus or minus root of minus 3 by 2. So minus 1 plus or minus I root 3 by 2. Right? So I'm going to call this as minus 1 plus I root 3 by 2. I'm going to call this as omega minus 1 minus I root 3 by 2. I'm going to call this as omega square. So set of all solutions of this is, so G consists of 1 omega omega square. Right? 1 omega omega square. What is omega? Omega is minus 1 plus I root 3 by 2. And omega square is minus 1 minus I root 3 by 2. So this forms an abelian group with respect to this. This has only 3 elements here, right? All the 13 examples has infinite elements in G, but here it has only 3 elements, right? Okay, here the operation is multiplication, right? With respect to multiplication. So note that omega cube is 1, right? You just, very simple, this is omega square. You just multiply omega and omega square, you will get 1. Just multiply omega and omega square. Multiply these two complex numbers, you will get 1. You can check it out, right? So this forms an abelian group. So whenever you need to tell whether a finite group forms a group or not, you need to put Cayley's table, right? Whenever you have a finite group, in order to say it satisfies closure, associative, ID, inverse, you need to put Cayley's table. So for Cayley's table, what you need to do is you need to put Cayley's table first, right? So you just put the elements here, 1 omega omega square. Just put the elements here, 1 omega omega square, right? Now you multiply this, right? Just multiply this. 1 into 1 is 1. 1 into omega is omega. 1 into omega square is omega square. Omega square into 1 is omega. Omega into omega is omega square. Omega cube is 1. This is omega square 1. Omega power 4. So omega power 4 is same as omega, right? Because omega cube into omega. Omega cube is 1. So it will be 1. So this is the, here you need to put operation. Operation here is multiplication, right? Just put operation here. Just put the elements horizontally and vertically and fill the table, right? Now you can see, you need to check all the condition. So it is closed, right? So for all, you can see this is the set of all output elements. All these output elements is in G. That is the beauty of Cayley's table, right? These are the output elements, right? For all a comma b in G, a star b has to be in G. A star b is nothing but these 9 elements. All possible 9 elements. All these are in G. So it is closed. And what about associative? Again, it is true, right? And for identity, E is equal to 1 is the ID element. So you need to write definition. I'm not into the definition, right? Because 1 into 1 is 1, omega into 1 is omega, omega square into 1 is omega square. If you multiply 1 with this, and 1 also is in G also. Okay. What about inverse? See, for inverse, you need to find for each element. So what is the inverse of 1? What is the inverse of omega? What is the inverse of omega square? What is the inverse of 1? 1 into what is 1? It is 1 only. Omega into what? See, inverse of omega is omega square. Because omega into omega square is 1. What is the definition of inverse? A star, A inverse has to be 1. Here star is multiplication. So omega into what is 1? Omega into omega square is 1. Omega square into what is 1? Inverse of omega square is omega. So you need to write down the inverse for each of its element if it is finite. Is it clear? 1 into 1 is 1. Omega into what is 1? Omega into omega square is 1. Omega square into what is 1? It is omega. So that means you need to write down inverse for each of its element. Is it clear? So this is an example of a finite group because you can see the set G consists of only 3 elements here, right? And similarly, you can also construct a group G with 4 elements. Similarly, you can set up all solutions of solutions of z power 4 is equal to 1 with respect to multiplication forms and abelian group. This is the fourth roots of unity. This is fourth roots of unity. Yes or no? This is fourth root of unity, right? So what is fourth root of unity? You just have to solve this, right? You can easily solve this, right? You need to solve z power 4 is equal to 1. So this implies z square whole square minus 1 square is 0. So a square minus b square. So a plus b, a minus b. This will give you I and minus I. This will give you 1 and minus 1. So therefore, your set G consists of 1 minus 1, I minus I. Right? So these 4 elements again with respect to multiplication forms a abelian group. So construct an Cayley's table. After that, you say it is closed associative. Uh, you just say it is closed associative and so on. So just write Cayley's table first. So operation is multiplication. 1 minus 1, I minus I. 1 minus 1, I minus I. So 1 into 1 is 1 minus 1, I minus I. And this will be minus 1, I minus I. So minus 1 into minus 1 is plus 1, minus 1 into minus I is plus I. So this will be plus I. I should be minus I into I is I square is minus 1, minus I square which is plus 1, minus I, this will be plus I, minus I square is minus 1, plus 1. Now you can see all these output elements are in G only, right? So it is closed, it is associative. And what about existence of identity? Again, E is equal to 1 is the ID element because 1 into 1 is 1, minus 1 into 1 is minus 1, I into 1 is I, minus I into 1 is minus I. And for inverse, you need to write down for each of its element if it is finite group. So what about inverse of 1? What about inverse of minus 1? Inverse of I, inverse of minus I. What is inverse of 1? Inverse of 1 is 1. Minus 1 into what is 1? It is minus 1. I into what is 1? It is minus I. Minus I into what is plus 1? It is plus I. Right? So this is the inverse. Right? Closure means you write out a definition that for all A comma B belongs to G, A star B is in G. So in general, so this is fourth root of unity. So this is a finite group with 4 elements. This is a finite group with 3 elements. Similarly, you can construct any group with n elements. What are those n elements? It is nothing but the solutions of z power n is equal to 1. Very important, right? So that means in general, let it out here, very important. In general, the set of all nth root of unity, nth roots of unity, that is z power n is equal to 1, forms an abelian group with respect to multiplication. It is abelian also. because it satisfies commutative property. That means it will be abelian also, right? Thus forms an abelian group. So that means you can construct a set G with n elements, whatever you want, and that will form a group. You can construct a set with two elements. Z square is equal to 1. So 1 and minus 1. That two elements will form a group with two elements. 1, a set with only one element. Just take 1. That will be a group. 1 minus 1. That will be a group. Solutions of Z cube is equal to 1. 1 omega omega square. That will be a group. All these are finite group, right? So if you want to construct a group with 10 elements, you just take the solutions of Z power 10 is equal to 1, right? Okay, is it clear up to now? Is these two examples of finite groups are clear? Okay, so we'll move on to the next example of finite group. See, next is called addition modulo n, right? Addition modulo n. Sorry, addition modulo n is very important. Zn with respect to addition modulo n, right? This is also you can construct. See, if you want to construct a group with 10 elements, you can find the solutions of Z power 10 is equal to 1. If not, you can construct this group, right? I'll give an example. Let us take Z5, right? So Z5 will have 0, 1, 2, 3, 4. So in general, Zn will have 0 to n minus 1, right? Zn will have 0, 1, 2 up to n minus 1. So Z5 will have 0 to 4 and this has 5 elements, right? Okay. Now you need to, this will be an abelian group with respect to addition modulo n. Usually we have seen only addition and multiplication and addition binary operation. Now we going to have multiplication modulo, sorry, addition modulo n. The operation is addition modulo n. So whenever you have a finite group, it is addition modulo n, right? So it is 0, 1, 2, 3, 4, 5. Sorry. Here we have 0, 1, 2, 3, 4. See, you just need to add it up. If that number is greater than or equal to 5, you need to put a remainder, right? So 0 plus 0 is 0, 0 plus 1 is 1, 0, 2, 3. If it is greater than or equal to 4, put the remainder. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, 0. If it is greater than or equal to 5, put the remainder. 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 5 is 0, 2 plus 4 is 6, 6 divided by 5 gives a remainder 1, right? 4 plus 3 plus 0 is 3, 3 plus 1 is 4, 3 plus 2 is 5, 3 plus 3 is 6, 3 plus 4 is 7. 7 means 2 because you put addition and then modulo n. Modulo n means you put the remainder, right? So 4 plus 0 is 4, 4 plus 1 is 5, 4 plus 2 is 6, 4 plus 3 is 7, 4 plus 4 is 8, that means 3. Now you can see these all these output elements again all is in G, right? All are in G. So that means again it is closed. This for example, right? I have taken n to be equal to 5. So in general, it is true for all n. So it is closed because for all a comma b belongs to G, A addition modulo n, B is also in G, right? See, this is addition modulo 5. Need to put 5 here. So it is in G. And again, it is associative also. And what about ID element here? E is equal to 0 is the ID element, right? Because if you add 0 with that, and if you perform addition modulo n, it will give you same number only. So E is equal to 0 is the ID element. And what about inverse? We need to write down for each of this element. Existence of inverse. Existence of inverse. So inverse of 0, inverse of 1, inverse of 2, inverse of 3, inverse of 4. So 0 into what is 0? 0 into 0 is 0. 1 into what is 0? 1 into 0 is, sorry, 1 into what is 0? It is plus only, right? 1 plus what is 0? 1 plus 0 is 0. 2 plus what is 0? So 2 plus 3 is 0. Because 2 plus 3 will give you 5. 5 is same as 0 here. Here 5 acts as an ID element, right? 5 acts as a 0 element. What is inverse of 3? 3 plus what is 0? So what is the definition of inverse? A plus A inverse has to give you 0. So if you take 2, 2 plus what is 0? So 2 plus 3 is 0 because 2 plus 3 is 5, 5 is 0. What is 3? Inverse of 3? 3 is 2. Inverse of 4 is 1, right? It means that 2 plus 3 is 0. It means that 3 plus 2 is 0. It means that 4 plus 1 is 0. And about it is also commutative also. So addition model forms and this is the best example of constructing a finite group of order n. So if you want to construct a group of order 3, you just take Z3. Z3 with respect to addition modulo. Or you can also take cube roots of unity, but this will be uh, very good, right? Voice is not clear. Is it clear only, right? Voice? The voice is clear? Yes, sorry. Inverse of 1 is 4. Because 1 plus 4 is 5, 5 is 0. Sorry. Voice is clear, right? See, these three are finite groups, right? It is satisfies commutative property also. A plus B is same as B plus A. Now we'll move for fourth example. So still we are going to do many examples, right? So as of now, in infinite group, I have given you uh, 13 examples, and in finite group, I have given you 3 examples as of now. Very important, very important, right? I'll be using this group for many of the theorems example. In order to explain the theorem, I will be using this group Zn with respect to Zn with respect to addition modulo n. Multiplication modulo n doesn't form a group. Addition modulo n forms a group. Multiplication modulo n doesn't form a group, right? You just take this exercise, right? Instead of addition, you just multiply and write the remainder. If that number is greater than or equal to n, it will not form a group. You just tell me, analyze why, right? Zn with respect to multiplication modulo n, respect to multiplication modulo n, multiply 2 into 2 is 4, 2 into 3 is 6, that means that will give you 1, 2 into 4 is 8, that will give you 3, right? Just take this as exercise, right? Multiplication model n doesn't form a group, take this exercise, right? You just take a counter example, right? You just take Z5, take same Z5. Instead of addition, you just perform multiplication. You will have some output elements. You see whether all the output elements is in G, and you see whether ID element is there or not, and you see whether inverse is there or not. Right? You will not have inverse. Okay. So addition modulo n is over. Fourth group is the set UN, the set U of n, the set U of n, right? So what is UN, right? I'm going to define a set UN. UN consists of UN consists of all those x in integer, all those x in integer, such that x lies between 1 to n, 1 to n, quickly n, and GCD of x comma n is 1, right? That is all those x in integers such that x lies between 1 to n and GCD should be 1. That is all those, they should be co-prime. All those x in n with respect to multiplication. With respect to multiplication forms. See, I'm going to give you lots and lots of examples. I'm going to give you almost 25 examples. You have very clear idea about this, right? With respect to multiplication, I'm going to give you some unique examples also that you will not find in all textbooks. So all those x in integers, x lies between 1 to n and GCD of x comma n is 1 with this multiplication forms and forms and abelian group with respect to, see, here I'm going to forms an abelian group with respect to multiplication modulo n. Zn is not a group with respect to multiplication modulo n, but this set will be a group with respect to multiplication modulo n, right? See, the previous example I have given you Zn with respect to addition modulo n forms a group, but Zn multiplication modulo n doesn't form. Okay, I'll write it down note here. Zn with respect to multiplication modulo n not a group, but this set with multiplication modulo n will be a group, right? I'll give you an example. Let us take u10, right? For example, construct u10, right? What is u of 10? So all those x in integers such that 1 is less than x is less than 10, such that GCD of x comma 10 should be 1, right? So you collect, see, all the numbers between 1 to 10 such that GCD of 1 comma 10 should be 1. So surely 1 will be there because GCD of 1 comma 10 is 1. What about 2 comma 10? 2 comma 10 GCD is 2. So 2 will be not there. What about 3 comma 10? It is 1 only. So 3 will be there. So you just collect all those numbers that are less than n and GCD should be 1. Or you can also put natural numbers here. That is not a problem because x lies between 1 to n, right? Okay. So 3 comma 10, 4 comma 10, no, because GCD is 2. 5 comma 10, GCD is 5. 6 comma 10, GCD is 2. 7 comma 10, yes, because GCD of 7 comma 10 is 1. 8 comma 10, GCD is 2. 9 comma 10, yes. 10 you should not put here because it has to be strictly less than. So this consists of 4 elements, right? Now this forms a group with respect to multiplication modulo n. So it is multiplication modulo n, right? last year, right? So we have 1, 3, 7, 9. 1, 3, 7, 9. 1 into 1, 1 into 3, 1 into 7, 1 into 9. 3 ones are 3. 3 threes are 9. 9 modulo 10. 9 only. Right? It is mod n is 10 here. 3 sevens are 21. 21 mod 10. 1. 3 is a 27. 27 mod 10. See, you can see how beautiful it is, right? All the outputs are again from 1379. 7 ones are 7. 21. 49. 49 means 9. 63 means 3. 9 ones are 9. 27 na 7. 63 means 3. 81 1. Now you can see all these output elements are in G. So it will be closed. It will be associative. And what about ID element? E is equal to 1 is the ID element, right? Because 1 into 1 is 1, 3 into 1 is 3, 7 into 1 is 7, 9 into 1 is 9. And what about inverses? Inverse of 1, inverse of 3, inverse of 7, inverse of 9. Inverse of 1 is 1, inverse of 3 is 7 because 3 into 7 is 21, 21 mod 10 is 1. Inverse of 7 is 3, inverse of 9 is 9. Right? So these are the inverse, and also it satisfies commutative property also. So that means this set un with respect to multiplication modulo n forms an abelian group, right? So we'll stop here, right? So we have seen 13 examples for infinite group and 4 examples for finite group. So still I'm going to give you lots and lots of example until you get annoyed, right? I'm going to give you lots and lots of examples. The next class we'll be discussing about client 4 group, quaternion group, dihedral group, permutation group, alternating group, um, GLN, R, SLN, R, matrix group, right? Power set group. I'm going to give you lots and lots of example, and everything will be very easy for you. The higher concepts, right? So in this class, we have seen 13 examples of infinite group and 4 examples of finite group. So if you want to construct a group with 10 elements, take Z10 with respect to addition modulo n. If you want to construct a group with 4 elements, take Z4 with respect to addition modulo n. See, if you want to construct a group with n elements, always go for Zn with respect to addition modulo n. Or you can also go for nth root of unity also, but it will take time to find the roots. So always go for Zn. If you want to construct a finite group of n elements, take Zn. It is abelian, right? And for infinite group, there are many examples I have given you. So in the next class, we'll continue more problems, more examples for groups. So the conclusion is we have a set G, we have a binary operation, right? We have a set G, we have a binary operation. If that set G satisfies closure, associative, ID, and inverse, we say it is a group. If it satisfies commutative property also, we say it is an abelian group. Very simple, right? So in exam point of view, they will give you a set, they will give you binary operation. If you want to say it is a group, you just say it satisfies closure, associative, ID, and inverse. And if you want to say abelian, you just say it satisfies commutative property also, right? So next class, we will solve more examples, right? So thank you. If you have any doubt, you can ask or else we will wind off. GCD repeat. See, greatest common divisor is the 7th standard level, right? See, this is what is GCD means GCD should be 1. So you just collect all the numbers from 1 to 10 whose GCD is 1. So 1 comma 10 GCD is 1, 2 comma 10 GCD is 2. See, this is a 9th standard level concept, right? GCD. 2 comma 10 greatest common divisor is 2. 3 comma 10 greatest common divisor is 1. 4 comma 10 greatest common divisor is 2. What are the divisors for 1? What are the divisors? See, if you want to find GCD of 4 comma 10, what is the divisors for 4? 1, 2 and 4. What are the divisors for 10? 1, 2, 5 and 10. So what is the greatest common divisor? 2 is the greatest common. It has to be common and it has to be greatest also. So GCD is 2. So list down all the divisors and see which is common and greatest. So GCD of 4 comma 10 is 2 and GCD of 5 comma 10. So devices of 5 are 1 and 5. Devices of 10 are 1, 2, 5, 10. So common and highest is 5. So GCD is 5. If GCD is 1 only, we need to put that in the set. So 5 should not be here. 7 comma 10 GCD is 1. 8 comma 10 GCD is 2. So in that way, you need to collect all those elements whose GCD is 1. Now multiplication modulo n. Multiply and write the remainder. So it is 10 here, right? 1 into 1, 1 into 3. 3 threes are 9. If it is less than or equal to 10 means you write that around. If it is greater than or equal to 10 means you need to put the remainder. 20, 9 is 27. 27 mod 10. So 27 divided by 10. Remainder will be 7. 7 is 21. 21 divided by 10. Remainder will be 1. 7 9 is 63. 63 divided by 10 will be having a remainder as 3. So in that way it forms a group. Addition modulo n is you need to add. So 0 plus 2 is 2. 1 plus 0. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. If it is 5 means if it is n or greater than or equal to n means you need to put the remainder. If it is greater than or equal to 5 means put the remainder after dividing by 5. Right? Very simple. So next class we'll continue more examples. Right? So thank you. All the best.